Cool, let's go. I'd like to open with a question. Who of you has been to Andrew Sutton's talk about reflection earlier this week? It's about a third of the room. So those of you who have seen it, you will hopefully know by the end of the session what cool things we can do with reflection. But I'm getting ahead of myself. First of all, who am I? I'm a consultant living in Berlin, working mostly on embedded systems and other systems programming tasks, such as device drivers, kernels, and firmware. And I have this very specific requirement sometimes that I want to have very reliable code or very performant or resource-saving code. And I think C++ really has an edge over other programming languages here because we have these facilities for zero-cost abstractions that allow us to combine type safety without any performance loss while working really, really close to the hardware. And that's kind of what I specialize in. So, yeah. On the less serious side, though, I try to work on a game console emulation whenever I have some time. So some projects worth noting is Dolphin, the Nintendo GameCube and Wii emulator, as well as PPSSPP, which is a PSP emulator. If you're interested in that kind of stuff, you can follow me on Twitter or check my website. And yeah, before we dive in, there's a small disclaimer I like to make, and that's the CppCon bingo. Anyone seen that one yet? Yes. You can check Bryce's Twitter for the original source, Bryce Lelbach. And there are a couple of cells I need to cross off right in the beginning. So first of all, probably noticed by now, this is yet another hipster presentation using Reveal.js. Sorry. We will be talking about zero-cost abstractions, and there will be complaints about exceptions. And also, as I just noted before already, there will be assurances, in quotation marks, that reflection will be in the next standard. And apparently we have cherry code. Cool. So Peter got bingo, so we're good. Anyway, that aside, let's dive into it. What's the problem that we're trying to solve today? The problem that we're trying to solve today is binary serialization. And what do I mean with that? Let's consider a user-defined C++ structure called just myDataType, which has three fields: a 32-bit integer, an 8-bit integer, and another 32-bit integer, with some values, and for one reason or the other, we want to encode these values in a binary stream, or more specifically, in a compact binary encoding. And that comes up in a couple of places. So two example use cases I found is networking, where some Alice might be trying to talk or to communicate with some Bob, and they both use the same program, the same underlying data structures. But obviously, C++ data structures isn't what we send over the wire or over Wi-Fi. What we send over the wire is a binary stream. So we need to have some way of turning our source data into this binary stream. That's what Alice needs to do, and vice versa. Bob needs to find a way to decode this binary encoding back to the original data type. Another use case is file parsing and saving, where if you look at most common file formats such as MP3, bitmaps, PNG files, whatever really, I usually start with well-defined and well-specified static headers that contain the metadata about the file. And to make this a little bit more concrete, let's look at bitmaps. Bitmaps are actually made of a very simple structure. They start with two headers followed by the actual data. So what does that look like? On the first hand, we have the primary header, which contains, first of all, an identifier, which must be BM. If it's not BM, we immediately know it's not a bitmap file. So this is kind of a signature. Sometimes people also call it a magic word. And yeah, it just tells us what kind of file it is. And then there's other information, such as the general file size or the offset to the data that we want to load. And this is typically what we'd see in a specification. But we don't just use specifications, we also want to model them in terms of C++ code. And how we might want to do that is using a simple structure, which just the equivalent fields from the specification translated to 16-bit or 32-bit integers. Similarly, the secondary header contains a little bit more info about the actual image, such as the image dimensions and the number of bits per pixel. which again we might want to translate using a kind of secondary header structure in this case. One interesting bit is the compression field right here. This indicates what kind of compression algorithm is used for the bitmap image. So either we use no compression at all and just store the pixel data verbatimly, or we use some sort of runtime length encoding or any of the other supported types. And the way we can model that one best is using an enum, of course, where we just say first type is an none, and then the others are the runtime length encodings, etc. And then finally, we got the actual data blob in the image, which assuming we've got 24 bits per pixel, for instance, we might just represent using a structure where each component is represented by an 8-bit integer. So that's the setting for this talk, and you might already have some idea of how you would personally solve the problem, right? It's not exactly rocket science, but for one reason or the other, I feel like most standard solutions to this problem are non-solutions. I'm not saying they won't work, but I will illustrate some weaknesses as we go along the way. And the first such kind of non-solution is the memcopy approach, which need not actually use memcopy, but you'll see why it's called memcopy in a second, where we just stack allocate our desired headers, then cast them to a plain char buffer, and then read the data from our input file just on top of them. So it's called memcopy approach because that's what memcopy does under the hood, right? It just casts your entity to a char buffer, then writes the data right overhead. And well, let's see how well this goes. I've set up an offline instance of Compiler Explorer, because you can do that, which is really cool. And you can see we have the same setup as illustrated on the slide. So we got this BMP header and the compression enum and the secondary header. And we got an F stream pointing to some local file on my disk, as well as the memcopy-esque approach shown on the slide. And you might notice, so this at the bottom right, this is the output of the program once I compile it. And it's kind of weird. So maybe I just picked an image where the data offset is, for some reason, 0x that many bytes past the secondary headers, which would be weird, but it could be feasible. And maybe, just maybe, my file is indeed that large in terms of the image size. But well, it's not. It's not. And so how come our image is doing this kind of, how come our program is reading those kind of dimensions? Well, the issue is, if you look at the BMP header, we've got a 16-bit member followed by a 32-bit member. And what the compiler will do here, for performance reasons, is we'll implicitly add a uint16 integer for padding purposes. So that means when we just straight up read the size of that BMP header from our input file, we accidentally skip 2 bytes that we're not supposed to skip, as per the specification. So in other words, the specification is not correctly modeled in our C++ source code right now. And there are a number of ways to circumvent that kind of problem. And the most common approach is to use a compiler directive, pragma-pag, which I believe only works on GCC and Clang. MSVC has their own thing. And using this directive, there will be no implicit padding here anymore. As you can see, the image headers are indeed now read incorrectly, and we get the correct data offset as well as the correct image size that would be expected. So this is the first kind of weakness these kind of approaches have, is that you gotta be really, really careful about how you model your static data structures in the C++ source code file. But there's a different drawback to this, in that it doesn't actually work for all data types you might imagine. There's an implicit requirement of using memcopy or file read, in that it only works for reasonably C-like structures. So if your data type has a virtual member function, or maybe just a non-trivial constructor, this memcopy approach is not guaranteed to work anymore. So, and the really bad part about it is nothing about this is being checked. If anything, if you have a virtual member function, it will just corrupt your vtable and you won't be like a compiler won't even warn about you. So you need to go down and actually debug the issue, which probably is easy to find, but in my book, it's an unnecessary issue to consider. Next approach, type bonding. So this is kind of memcopy version 2, in a sense. In this approach, we allocate a jar buffer on the stack and read our data into it. And then we do something nasty. We just reinterpret cast the buffer to our desired header types. Now, this isn't really any different in terms of semantics, in terms of the expected semantics from the memcopy approach. So you will still have the same implicit padding issues as you had before. But there's something else. It's not actually valid C++. In some fields, this is perfectly standard code to write, though. Especially embedded systems just want to get optimal performance out of this and just say, OK, whatever, I'll just turn off compiler optimizations, and then it'll be fine. If that works for you, help yourself. But I personally have run into multiple issues with that kind of approach in different projects. And if compiler optimizations break your code because you're using reinterpret casts like that, this is not a fun issue to debug. You can waste literal hours into that, literal days sometimes, and you won't find the issue. So, yeah. If you have no idea what I'm talking about, check the CPP reference. It will explain quite clearly what you can do with reinterpret cast. Right. Luckily, C++20 gives us a better option called bitcast, which is kind of a merger of the best of the two worlds we've seen before. And the idea is you use jar buffers, just like in the reinterpret cast approach. And then you read your data into those. And then you use something that looks like a reinterpret cast, but it's called a bitcast. And what it will do is we'll do what you'd normally expect from reinterpret casting, but in a well-defined way. In a well-defined way. And this will actually also verify that the assumptions about the types that are being made, such as that it needs to be C-like, are actually being met. So that's quite cool. In terms of semantics, though, all of these three examples are pretty much equivalent. They all ignore the implicit padding, and that's kind of a pain point in my book. So the alternative is you don't use these automatic approaches. You just write it all yourself. So you read your data into a jar buffer. Then you start constructing the primary header. So what does it mean? Well, you read the first 2 bytes, stitch them together using some bit masks and bit shifting and the whatnot. You read the next 4 bytes, and the next 4 bytes, and the next 4 bytes. And then you're done. You've got your primary header. Yay. Oh, wait, there's another header, the secondary header. So this blows up really, really quickly, and it's clearly not scalable. On the positive side, though, at least it considers the implicit padding, so get this trade-off to make right. So small summary, these 4 approaches. We've seen that only the first 3 are really automatic in the sense that you just one-line the thing pretty much, and the boilerplate code just clearly isn't scalable. But on the other hand, none of these approaches other than the boilerplate solution consider implicit padding. There's also the issue that none of these approaches really validate the data you have. If you consider the primary bitmap header, for instance, we've got this magic word that needs to match the character string BM. None of these approaches verify such properties. And that's kind of annoying because after the actual deserialization code, we now need to go down and explicitly verify that the data that is already in our data type is actually valid. And that's not great because usually you want to have class invariants, depending on your context, and that just completely breaks that workflow. Yeah, the manual code kind of is an exception to this, but only kind of, because in my book, if I'm already writing 100 of lines of code for serialization logic, I certainly don't want to hide some validation logic somewhere in there. So, yeah. Non-trivial construction is another thing. If you have a constructor in your data, so if you don't just want to copy the binary stream onto your data type, but really want to invoke the constructor, that doesn't work with memcopy, because memcopy just copies it over your data. And none of the approaches other than the manual one really call any constructor at all. Const init. You cannot actually deserialize your data and have the resulting data type be const. Which, you know, for some people that works, but I like to reduce the error surface in my program, and hence I need to make as many variables as possible const. And well, if I need to stack allocate the object before even initializing it, that won't work. Type safety. The first two approaches, reinterpret cast and memcopy, did not check whether we actually have a C-like type. For manual code, this isn't even necessary, but bitcast at least does the check. So only the latter two approaches are type safe in my opinion. And then finally, reminder, don't use reinterpret cast because, well, it's not well-defined behavior. So yeah, this isn't really satisfactory in my book. So what can we do? We can look at what other languages do, because clearly we're not the first programming language on the planet to have this kind of problem. And the first language I actually looked at was Python. Python is a rather popular language. I try to not use it in my projects, but I will. And it has a library called construct. And construct is pretty much solving the problem that I've been seeing here. So what they have is actually this very interesting approach to declaring structures, where you don't just define your data fields and their size. Well, actually, you can do that. So first, you define your data fields here, and then you use this annotation kind of syntax, where you tell the library how large each of these fields should be in the serialized state. But what's more, and that's what I find really, really cool about this, is it allows you to state explicitly your expectations on the deserialized data right in the declaration of the data type itself. So not only do you get this declarative syntax, but it's all packaged in one kind of entity, which I find really, really helpful. So yeah, declarative syntax, annotations for serialization, and annotations for validation. Really nice stuff. And it actually goes a little bit farther than that. For the secondary header, you might remember the compression field. It has an annotation called Enum, which just says that this field, once it's being deserialized, it must be one of the values explicitly listed here. So by the way, the way you trigger a load then is just using this bitmapfile.parse command. And what will happen with the enum case? If the loaded field is not one of these enum values, you will throw an exception. You will throw an exception. And that's great, because that helps us hold up our class invariants. And well, obviously we got to make that check somewhere anyway. We want to detect if there is some compression algorithm in use that we do not actually support. So yeah, automatic enum validation. Really, really cool stuff. And that's where blobify comes into play. Blobify is a library I've been working on for, well, the past 2 months, I guess. It has actually been in development for much longer than that because it has been part of a project. But at some point I decided, okay, I want to turn this into a proper library so other people can benefit from that. And Blobify's declared goal is to bring constructs features over to C++. And I don't just mean this in the sense that I ported the library or anything, because first of all, that wouldn't quite work so easily. But really, I want to bring the feature set in a canonical way to the language that fits with the other language features we have. And what that means in practice, I now have a library that allows you to do automatic deserialization and serialization on your user-defined data types, while also enabling you to write down your expectations for the deserialized data using a built-in domain-specific language right in the code itself. And then finally, of course, we want it all to be type-safe. These headers are usually statically specified, so they should be modelable in C++ structures, so there's no reason to involve any kind of dynamic typing or anything like that. And then finally, I want it to be zero cost. This should be completely equivalent to handwritten code. I mean, the library as it is already avoids expensive stuff such as dynamically allocating memory or anything like that, but there is some overhead associated with it. But hopefully as time progresses, I'll be able to get rid of the cost there is today and yeah, make it equivalent to handwritten code. Right, it's a GitHub It's been on GitHub for a while, so if you want to check it out, you can download it today and use it in your projects. Although, with a disclaimer, it's still somewhat experimental, so maybe don't use it in production. What does it look like? The first thing you need to do as a kind of preparation step is you need to adapt your data source, such as a std_f stream or a network socket. You need to adapt that to Blobify's internal API so that it knows how to read and write blocks into the data source. And that's what you do with this kind of blob iStream storage thing. And this doesn't really do much. It's really just a thin wrapper around the fstream object in this case. Right, and once you have that, all you need to do, really, is to call a function called blob load and pass it the data type that you want to deserialize from the stream. Similarly, you just do the same. So what this does is it will read the data and skip ahead in the input source. So you can just continue loading another data element right after that. And this works pretty much, I mean, the way you write it down is pretty much as automatic as we would hope from the reinterpretcast approaches and bitcast approaches. But this one is actually equivalent to the handwritten code. And that's cool, because now we have something that respects all the implicit padding we have in our file, in our structure. It supports non-trivial constructors. You can have classes that transform the input data and maybe convert it into different units, for instance. And finally, you can use it to initialize constant variables. So yay for software design. And conceptually, you can think about this as a three-step process. First, it actually reads a number of raw bytes from the storage. Then it uses those to construct, and by that I mean a proper construction, the data type, and then it will perform some validation, which I get to in a bit. So of course there's a code sample for that as well. Let's see how it looks like. It's pretty much the same as before. We've got our BMP header, but note I'm not using any compiler preprocessor directives here. So indeed, we will have this implicit padding here. And we scroll down a little. This is what the actual Blobify deserialization logic looks like. So really, really simple stuff. And we just print out some fields as usual. And for comparison purposes, I also added the reinterpretcast variant here. I see on the right side, the top part is what Blobify reads from the file, and the bottom part is what is the incorrect result that reinterpretcast would get you because of the implicit padding. So that's cool. If you want to load multiple elements, that's also supported because, well, sometimes you just have a collection of elements that you want to load at once. And so, for instance, in our case, that might be the pixel data stored in the file. And the API to do so is called load many, and you pass it one template parameter, which is the collection type that you want to load. So this is not necessarily restricted to std vector. You could also pass it as std list or any kind of other container that implements the STL interface. So you pass it that collection type, and then as a second function parameter, you give it the number of elements it should be reading. So also got a small example for this, just like before, but now we have some code that reads the pixel data from our bitmap, and we see it's reading 32 times 32 pixels. That's the size of the return vector. And just for the sake of it, it prints some of the pixel values, but yeah. So we get our image out of that, and everyone's happy. Any questions so far?
You said it doesn't allocate memory, so how does the blob function actually, how does the blob function create a buffer for?
Well, okay, I should have qualified that. I mean, in the case of std vector, it of course needs to allocate memory, just because you're constructing.
Just for std vector, for the bitmap headers. So it first reads to a buffer, and then from that buffer, it constructs the appropriate object.
It just stack allocates them.
And what's the buffer size that needs to be read from the file? The size of the structure?
Sorry, I'm not sure what you're asking.
But probably some internal. So presumably this thing inside contains fstream read.
Mm-hmm.
What does it read it into?
Oh, right. It reads it into a stack internal buffer.
Which is the size of the template argument.
Something like that, yes. It might be somewhat smaller because the size of the template argument in this case
is bigger than the buffer.
Yeah.
Because of padding. Okay.
Yeah. But it would only read as many bytes from the buffer as would be necessary.
Okay.
Have you considered using type deduction and have it figure out the types for you so you don't have to tell it the types? It can actually calculate the size on its own then too?
So we get to that in a bit. The Serialization API does that.
Okay.
But for the load API, you got to tell it what kind of type it is.
Can't it pull it out of the stream when you saved it out? You stored the type and the size. So when you read it back in, you reverse engineer that.
For that, you would have to have some sort of
Runtime reflection.
Right. We'll talk after I've done it.
We can discuss that later. I think what you're getting is that you're writing you're serializing your data into an object, and then you want to deserialize it. So to the programmer, there is not really any. It's kind of redundant because you're serializing the data and you just want to get it out. So why would you need to specify it again? That's the point you're getting at, right?
Right. Well, I serialize it to a file or a stream, but yeah.
Yeah. Let's talk later.
Does it work with bit fields?
I believe the short answer is no, but there's a different library I'm working on that actually replaces C-bit fields with a better solution. So in my case, that actually works fine because I'm using that kind of other abstraction, but I don't think it works with C-bit fields, but that's mostly because I haven't really tested it so far.
When you load binaries, do you load in little or big engine?
We get to that in a bit.
What?
We get to that in a bit.
I came late, I might have missed it. Is asynchronous read supported?
That's not something I've thought about.
Okay.
Interesting. I mean, you can always spawn a thread and do it yourself, but you would probably want something that does futures or something like that. Interesting, I'll think about that. All right, let's keep going. So the deserialization and serialization API is one big part about Blobify. And it's probably the easiest part for selling the library to people, but there's actually a second really big part about it, and that's the validation API. That's the part that takes care of making sure the data actually looks like something what we'd expect. And validation is implemented using this domain-specific language called properties in Blobify. And the way it looks like is a little bit strange, but try to keep an open mind until you see what it can actually do. So what we do is, right underneath our data type definition, we define a free function called properties. Now, this function must be const-expr, for reasons we'll see later. It takes one parameter, which is a tag type, that tells the library which data type we're talking about. And in there, we must initialize an object called property of type properties t, which will contain all of the expectations we have, but we'll see how that looks like in a bit. So we initialize that, next slide, and then we just return it to the caller. So what the library will do with this information is it will call that function for each of your data types, then extract the properties t information and add the appropriate validation logic automatically. And one example of this is this magic constant problem, right? Our primary header contains the signature that we need to compare against the constant 0x4d42, which is the byte string bm in a binary encoding. And the way that looks like is we just use this member function of properties t to specify we're talking about the member signature. And for that specific member, we want to set the property expected value, and we set that to the particular value. Looks complicated, but let's see it in practice. So you can see it's really just no changes at all to the data type itself. There's just a free function right next to it. And of course, in this case, we're doing, so actually, by the way, the actual reading logic is completely unchanged, so that all happens automatically. But in this case, of course, we don't see any difference because, well, I'm feeding it a valid BMP file, so of course, nothing really changed visibly. So let's pretend for a second that we didn't expect 0x for D for 2, but for D for 1. What now happens is that Blobify detects this mismatch between the expected value and the actual value that is loaded from our structure. So it throws an exception of type unexpected value exception, telling us what specifically went wrong. But what I find really, really cool about this design is it actually even tells us which particular member of the data type caused the error. Because, of course, we might have more than one single validation requirement. We might also want to, well, let's say we expect that the data offset is at 5, just making up a value here because it doesn't really make sense to have that kind of restriction anyway. And in this case, it wouldn't be the signature that fails, but rather the data offset validation that fails. So that's really, really useful if you want to have very fine control about how you handle errors in your validation logic. But rest assured, if you just care about did an error happen or did it not, you can also do that quite easily in Blobify because there's an exception hierarchy that you can just catch the most general exception type form. Right. Whoops, what am I doing? So that's not the only way we can specify these validation requirements, though. And this is actually a semi-experimental feature I added recently to an already experimental library. Oh well. And that's that you can add validators to your properties. And that's what you would use if you need more specific restrictions than an actual equality check. So maybe what you want to do instead is you want to say that the value should be less than a given number. This doesn't quite work yet because I didn't include the right file. And this doesn't work yet because this doesn't actually work with C++17 yet. Right. So now it checks whether the value that we read from the file is less than the given value 10. You can check that it works by just adding something really ridiculously large, and now it passes. But that's not the only thing we can do. We can also say blob require and give it a lambda function. So in this case, I want to say that the value should be less than this really, really large value, and it should be even, or any kind of other more complicated check than that. So you can see, thanks to the composability of these predicates, you can get really, really flexible validation checks, depending on what your use case specifically might be.
Can be less than byte size?
What's that?
To refer to members of the structures. To members of the structure.
So I didn't quite catch the question.
In the validators, can you refer to other members of the structure that's being deserialized?
That doesn't work yet. The question was if you can refer to other elements in the structure, such as the signature. So could you read the signature value from within this lambda, for instance? Right. That's not supported currently. It's a problem I'm aware of, and I'm thinking about how to solve though. Right, so that works. And the next kind of thing, so I've been coming up with this mechanism and figured, okay, what other kind of properties could we add? And the next thing that came to my mind was, hey, let's do regular expressions. So there's another property called matchregex, which you can give a regular expression and it will automatically compare the right value to this regular expression. Now, for this to work, I actually needed to change the signature member to HR buffer though. But other than that, you can just write that down like this. You can see I can change BM to B period. Okay, so regex is rather slow to compile currently. I'm not sure why that is. So you'll just have take my word on that this works, I suppose. But I can change this to A, and we'll get back to this in a minute, I guess, once it's done compiling. So this works. The next thing is, what you can do, and this hopefully will blow your mind, is it can actually validate your enum values. So you define your enum just like usual, then you set the property validate enum. And this will cause Blobify to automatically check if the value read from the file is indeed one of those listed values. Still compiling. Okay, I have to close. No, never mind. Right, so I'm setting this property on the secondary header at this point because that's where the enum is located at. And again, I'm feeding it a valid bitmap file, so nothing interesting really happens. So let's pretend for a second we didn't know what no compression meant. And you'll see it will just throw an exception. In this case, it will tell us it's an invalid enum value for the compression field. And yes?
Is a validate enum not the default?
Come again?
You said validate enum equals true. Is that not the default?
It's not the default, no. Because first of all, it doesn't work for all enum values. Well, it works for all enums, but sometimes you don't want to strictly have the value contained in the enum. Because you might have a different field kind of layout, such as this, where you use bit masks that can be combined in reasonable ways. Perhaps not in this example, but...
That's enum abuse, though.
Pardon?
That's enum abuse. It's really bit field, not a...
It's quite common, though.
Not mine.
Unfortunately, but
yeah.
That's what it is. And in my case, personally, I actually would use the enum validation less often than I would. Right. So that works. There's a couple of other properties. There is a way to, so that's a question that came up before, where you can specify whether the data should be loaded from a little endian or a big endian format to the host endianness. So Blobify will automatically convert the endianness on the fly for that. We've seen that one. And you can have some sort of size consistency checks, which isn't strictly necessary, but I found it useful in my case because I often have specifications that I look at and then model them in C++ code. And even though my serialization logic takes care of the implicit padding, sometimes these structures can get really big. And I make a small typo or whatever, and suddenly I forget a certain member in the structure or something. And that's when it's really useful to just put the total size of the structure as given in the specification as a property, so that it will be cross-checked automatically and make sure that the actual structure that I'm defining matches the specification. Right, so as a quick overview, we've seen that the load API allows you to do automatic deserialization. Also for runtime-sized collections, you can validate your data using these predicate requirements, but also using the more sophisticated validators, where you can even pass in lambdas to validate your data. You can use regular expressions, and you can validate enums. So yeah, that's quite cool and powerful in my opinion. Now, this has been all about loading, but of course the other way is implemented in Blobify as well. So in this case, we are talking about the Blobstore API, which is just mostly symmetric, just that you don't even need template parameters in this case, because you're already specifying the type as a function parameter, so it can just infer the type automatically. Right, so what I did in this case was I just read an input file and then wrote out the input headers verbatimly without any change. And then I randomized the pixel data and stored it back into the file. And the kind of output I get from that, well, as you'd expect, is just this kind of funky rainbow color thing, because we randomized all the pixel data, so that's precisely what we expect. So, yay. And yeah, conceptually, you can think about it as converting each of the elements in your structure to an integer type, which we can then cleanly serialize. And I'm not sure if I mentioned this at any point before, but all of this, by the way, also works in a recursive way. So if you have nested structures and structures that are nested within the nested structures, Blobify would just traverse it all from top to bottom and do the right thing. Right, so that's what the library can do. And you're probably asking yourself, how does it actually work? Because this is quite a lot of magic that has been happening so far. So I can't really get into the full details, but if you want to know the full details, I recommend reading the actual library source code. Other than the funky voodoo that goes into making all of this work, it's relatively readable, actually. But yeah, let's look into some of the building blocks. And the biggest building block so far is the library called MagickAdd. And MagickAdd is a library that allows you to turn C++ structures into std tuples. And you might be asking yourself, why is that a big deal? Well, it's a big deal because what I want to do in my library for serialization is I want to iterate over my user-defined structures. To serialize a full structure, I want to first serialize the first member, and go to the next one, serialize the second member, then the third, etc. But standard C++ just doesn't give me a way to do this. It just doesn't. MagickAdd allows us to turn this structure into a tuple. And what's great about tuples? Well, we can iterate over them. We cannot iterate conveniently over them, but it's possible thanks to template metaprogramming and other things. So, don't have a code snippet for that, but that's basically what it does. You can check out the library on GitHub, and the author of the library even gave a talk at Meeting C++ and elsewhere, where he illustrated the design of the library and how it works internally. If I recall correctly, it even works down to C++11, so that's super impressive in my book. Now, the trick that I'm using to turn the information I get from MagickAdd into actual functionality is variadic templates. Variadic templates is a C++11 feature that basically allows us to have type lists in a convenient way. So one thing I might have in my function is a load helper function. The load helper function is what I would call when I get the desired structure type from the user, and then a list of the members the structure contains from MagickAdd. I think this should be an autotype, actually. This is a typo. So what I do in this function is very simple, actually. I just start calling the constructor of the desired structure type. And what I put in there? Well, the values that I read from the file. So it recurs into a function called load_single, which loads a single object of the given file, of the given type. And then it uses this parameter pack expansion to duplicate this function call for each of the members in the structure. And then that's how all of this together forms a valid constructor call. And that's really all there is to it. Now, of course, it gets a little bit messy if you want to actually support nested structures. And it also gets a little bit messier if you want to support all the validation efforts. But the gist of it is that particular trick. So C++11's parameter pack expansions are what I'm using here on this slide. And 17 actually introduced fold expressions, which are also very useful in other kinds of stuff. So that's in particular what I use for the opposite direction for the store helper. If you want to learn more about how to apply this kind of stuff in your code, I've actually given a talk at last CppCon about this, where I go into much greater detail about this. Now, in the real world, things are never easy. So actually this kind of blows up a little. We have to use integer sequence. So this is because MagicGet doesn't give us a parameter pack, but rather it gives us a tuple. And tuples are somewhat more awkward to work with sometimes than parameter packs. So we need to use these integer sequences to make that work. But that's just a technicality, so don't worry about it. Right, so another point I wanted to talk about is design by introspection, which might be a little bit cryptic for now. But basically, you might have asked yourself, with all of these validation features that the library offers, how could I possibly claim that this could eventually be made into a zero-cost abstraction? Because if you think about it, the properties turn them off. The properties turn them on or off individually. So you would naively think that at runtime, at each serialization call, there would have to be some sort of check. Is this validation enabled? Is this enabled? Or is this enabled? But thankfully, I don't need to do any of that, because all of these checks happen at compile time. And how this looks like in practice is I've got this function called validate element that is run on each deserialized element of the stream, so of the structure. And it gets the member properties that you initialized in your properties function as a template parameter. And remember, the properties function was const expr, so that works. It wouldn't have been possible if that had some sort of runtime dynamic associated with it. Now, what I do in that function is, indeed, I check for each validation property whether it's enabled or not. But the trick here is I'm using an if const expr statement. And if const expr just evaluates the condition at compile time, and only if that is true, it will start compiling the body of that if statement. And that means if none of the validation properties are enabled, it will just throw away the entire code and compile the function down to a no operation. So that means no runtime checks happen here unless specifically requested by the user. Finally, MagicEnum. And MagicEnum is the missing piece I had to add to the library to make the enum validation magically work. I believe this actually employs much more magic tricks than MagicGet even, but it's a library, you just embed it into your project and you get the functionality for free. So what this allows me to do is just take a user-defined enum, and the library gives me the bounds of that enum for free, and that allows me to do the validation checks. It's also on GitHub. It's also experimental. I'm not actually sure which C++ standards it works with. 17, right. Yeah, and that's pretty much all there is to know about the library so far. Maybe a little glimpse to the future, what might happen in the future. So first thing I want to do is I want to have the library generate better assembly code, because currently it's kind of suboptimal in a lot of cases, but I think that's largely because it's in early stages and I already have some ideas on how to make it more optimal. Second thing is I want to add an exceptionless API. Because I'm quite happy, thanks to the audience, nobody here jumped up and ran out of the room when I said the library throws exceptions. So that's great. And for me personally, that's also totally fine, because all of the platforms I'm working on have exceptions. Even embedded systems that I work on don't really mind it too much because I just have the resources. But I can see that in some use cases, that's just not an option. Maybe you're working on an embedded system that's just way too small to even fit the exception runtime necessary. Maybe you're working in a low latency scenario that just cannot afford to have exceptions thrown at random positions. Or maybe you just work at a job where the coding guidelines tell you you cannot use exceptions. So there will be some alternative to that in the future. I'm not quite sure how it will look like, and I'm not sure if the same feature set can be provided, but it's on the agenda. And finally, I want to make MagicGet and MagicEnum opt-in. Because they're quite heavy, well, they're not heavyweight, they're rather small libraries, but I can see why people might not want to have two such experimental libraries in their code. And there's two options for this on how to replace these. The first one is the user might be required to provide their own own reflection logic by saying this is how, by telling Blobify, this is how you turn this data structure into a tuple, for instance. And this is actually what I'm using in the project that Blobify is used in internally. And the other option is, well, reflection. Because we're getting reflection, finally, hopefully, eventually. People say it might come in C++23. Let's see about that. But once we get reflection, we get all of Blobify's feature set for free. And it won't need any kind of adjustments to the API, because it's just built on reflection, whether it's implemented by MagicGet or MagicEnum, or the reflection TS itself. And that's where I see the potential of Blobify. Blobify tells us right now what we could possibly achieve with reflection in the C++ specification. Because that's such a question that I get so often. With all the new C++ features, such as reflection, yeah, sure, it sounds nice on paper, but what can we actually do with them? And Blobify is a constructive example of what can be done. So that's where I see the potential, and hopefully others might find that useful too. Right, so with that, let's conclude. We've seen the automatic serialization and deserialization code in the Blobstore and blobload APIs. We can have customizable validation logic where we can express the expectations of our data right in the code. And Blobify as a whole is a sort of sneak preview of what can be done with reflection. It's on GitHub. It's header only. It's C++17. That's the minimum requirement. And some of the more advanced features might require C++20 support, for which there are no compilers, but it will eventually. Yeah, GitHub link right here. And with that, I think we can hand it over to questions. Thanks.
Hi, can one extend the library with custom functionalities? For example, the load many loads a stud vector. And what if I have my own container class which has its own methods for construction and adding elements?
You can easily support custom collections by implementing the STL interface on them. So it needs begin and an iterator interface.
Okay.
All right, I have one question and one remark. The question is that when you saved that bitmap back out, you made a decision about whether or not those pad bytes should go into the file. And not every. I'm sorry?
It doesn't.
Right, but sometimes that a system would want that, sometimes they would not. I think that would need to be a point of configuration.
Yeah, you could have a property for that. You could say this particular member should have n bytes right after it as padding. That could be done.
All right, then the other, the remark is on data saving and loading. The thing that happens in serialization systems that complicates all of it is versioning. You'll trying to load old versions of data with newer code, and you'll probably want to have an answer for that if this wants to be the be-all, end-all solution.
Thank you. What about data types you supported? What kind of types these members can be? Not only integer, like Pascal's type, strings, or struct inside of struct?
So pretty much all user-defined types or types that have a constructor that can reasonably called with deserialized data. So that pretty much means either C-style data or data that takes an integer as its constructor argument. So it's
what about Pascal type string, where you have a string length and then a character set after that?
I'm not exactly sure what you mean by that, but we can talk about that later, I think.
Does it read the whole structure to a memory to deserialize, so it supports some streaming maybe?
So could you just repeat the question so I make sure I understood it correctly?
I'm wondering, does it read a whole structure into a memory that I read from a file, for example? Does it require it? Or I can read it by chunks, for example, the first fields, the second fields. For example, if you have a very big file, does it require to allocate the whole memory for a whole file?
So the load and store API I've shown, well, the load API I've shown requires you to allocate the entire structure that you're loading. doesn't require the entire file to be loaded into memory. But if your entire file happens to be described by a single structure, that's what that particular API would require. Now, there's actually a second complementary API in Blobify that I didn't present, which allows you to read individual members from a structure. And that might be what you're looking for. So you can selectively read individual members from their correct positions without having to seek to the appropriate locations. If anybody wants to research that offline, that's the lens load API in Blobify.
Okay, but you have demonstrated us only ways to read structures from a file, and I hope it supports reading structures from memory, from, for example, received by a network, etc.
So are you asking whether you can also use Blobify to decode data from memory? Yeah, you can do that. That's what the entire storage abstraction is for. So you're not bound to any particular storage medium. So you can read, you can deserialize from a file, you can deserialize from a network socket, or you can deserialize just from plain memory. And plain memory is actually my primary use case, in fact.
So often in a networking scenario, you're going to have a common header piece, and then you're going to decide what the rest looks like. And there's different ways to represent that. One way might be, I actually have a structure and I put the header as a component of that. That would seem to be something we can't do in this scenario.
Sorry, I didn't quite understand the question.
So if I have a struct, and one of the components of that structure is this common header, and then more members. I can't dynamically decide which kind of struct I want to instantiate.
Yeah, I don't think you could do that.
Would have to do that. You have to break it into different structures at that point, right?
I think so, but maybe we can talk about that later so I can make sure I understood the question correctly. All right, looks like that's all. So thanks again for coming and enjoy the rest of the week.